So today, first talk in this afternoon will be by Natalia Castellana on Quillen stratification theorems.
Okay, so thank you very much. Yeah, thank you very much, and thank you to the organizers for having me here. And this is a great opportunity, and so this is a fantastic place to be. And then I also thank them for their patience with me. So I didn't want to keep my title secret. It's just that I'm a bit, I'm not very, I don't deal very well with bureaucracy and these things. So I just failed to fill the right form. And I decided quite late because of the title of the program, Duality in Algebra and Topology. And all I know about, well, almost all I know about duality, I've learned from people who is giving lectures here. So I didn't know what to talk about. And then I decided to talk about Quillen stratification theorems. So today will be one, and then will appear versions of this theorem in later talks. The reason, well, the first reason is that I've been involved in a project recently that I've enjoyed a lot. So I'm happy to share some of the things I learned in this project, and involves algebra and topology, which is the second part of the title of the program. And I'll try to use the word duality in some of the lectures, but I think it will fit with the other lectures. So I think it fits with, already Henning mentioned Quillen stratification theorem yesterday morning as a motivation for the name of what's the stratification in another context. And it also relates with co-change, geometrical co-change at some point, and equivariant theory. So I'll do my best to fit with the other lectures. So Quillen stratification theorem. So today I want to discuss and explain a bit this paper. In fact, it's two papers of Quillen. It's called The Spectrum of an Equivariant Cohomology Ring. And there is in the first paper, there is a theorem called the F-isomorphism theorem, which I will devote most of the time today. And then in the second paper, he describes the spectrum of the spectrum of prime ideals of the cohomology of a finite group. And there are several proofs of the F-isomorphism theorem. The first one, the one that appears in this paper, is the one which involves more homotopy theory and geometry. Then there was another proof by himself and Benkov. We were more in the context of group cohomology from the homological algebra point of sight, which use some search theorem on the cohomology of finite group. I want to talk about the first one, which involves more geometry and homotopy. And because I want to do that, because there are some key ideas in this proof that I want to point out. And then I'm doing the exercise of saying which are these key points and how they could be generalized to other settings. Yeah, that's my goal, let's see. So it's about group cohomology. So since I don't know exactly the background, so I will do a very crash course on some important facts on group cohomology. Right? So we start with G. If it's not visible from the back, you can just tell me. Yeah? So in this talk, G will be a finite group. The theorem I'm going to talk about, the Quillen's theorem, works for compactly groups too, but I want to just focus on finite groups. So R, we take a commutative ring. And then with R and G, you can construct the group ring, which essentially you have formal R linear combinations of elements of G. These are the elements of RG. And the product uses the product, you play the distributive law and you just multiply the elements of the group and then you add coefficient Y. So that's, and M will be an RG module, which means that it's an R module with an action of G, which is compatible with the R module structure. That's all. And then what is group cohomology? Well, the answer is, well, depends on your what you like most. So if you're an algebraic topologist, you take G. and you construct a space out of G, the topological space, the classifying space BG. There are several models. You can do a simplicial model. You can take a free contractible space with a free G action and take the quotient. It's a KG one. There are several options. And then you look at the cohomology or ordinary cohomology in algebraic topology with twisted coefficients. Yeah. So you could take this as the definition of group cohomology. And or if you are from homological algebra, so you just take the X groups of Rm. Yeah. And they are the same. I already wrote two equalities, so they are isomorphic. They are the same because, well, the reason is that to compute these X groups, you need a projective resolution, and topology is giving you this projective resolution. Yeah. So you take EG, which is contractible and has a free G action. And then if you look at change of EG with coefficients in R, that gives you, because of EG is contractible and because the action is free, you have a free resolution of R by RG modules. And then when you just take ohms into M and compute kernels, co-kernels, blah, 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 what you get is, on the one hand, this cohomology. On the other hand, you just computed the X groups. Yeah, so just it's a RG resolution. Free RG resolution of R. So these are the same. And then depending in your context, sometimes it's better to deal with the topological space and the topological definition. Sometimes it goes better with the homological definition. So in my talk, I will just deal with trivial coefficients, right? So it's just a ring R with trivial action. Okay. And so that gives you a functor, right? So have a functor that goes from the category of groups. It's contravariant, and it lands in Reddit rings. Reddit commutative rings. Yeah. So if you look on the right side, it's just because the cohomology is a graded commutative ring. You have the cup product, and that gives you the structure. And if you look on the other side, these elements are given by n extensions, and then you just splice together n extensions, and it describes the product, and it's the same, right? So you land in graded commutative rings, and it's a functor. So if you have a morphism from H to G, that gives you a graded commutative ring morphism from the homology of G into the homology of H, right? I want to tell you the effect of one particular morphism. So let's say, take an element of G, and conjugation by this element gives you group homomorphism from G to G. Right? So H goes to, I'm very bad with conventions, so I'm trying to remember it's -1G. I might mix at some point. But, so this is a group homomorphisms, and we know what this group homomorphism induces in homology. And it turns out that this group homomorphism is the identity. One way of seeing it from the algebraic topology point of view is that the map induced by conjugation by G in the classifying space is a homotopy equivalent to the identity. Yeah? So, like this is homotopy equivalent to the identity, therefore it induces the identity in cohomology, right? So this will be important at some point. And but there are more structure for the cohomology. So there are not only morphisms induced by group homomorphisms. There is a morphism that goes the other way around. What I mean is that if you have K, a subgroup of G, there is a transfer map, a transfer morphism that goes from the cohomology of K into the cohomology of G. So if you, again, you are an algebraic topologist, the way of understanding this transfer map is because it's just a transfer for a finite covering. I mean, note if you have K subgroup of G, the map from BK into BG. Well, BK, you can have several models for BK. One point of the classifying space is that it's unique up to homotopy, but you have different models, right? So one model that you could take is that, well, you only need a contractible space with a free K action. But if EG has a free G action, it's also free when you restrict to K, right? So you can take EG mod K, and this is G mod G, and then the homotopy fiber of this is we have a finite covering essentially. So this you have G mod K. I mean the coset, and then there is a transfer for finite coverings, and this is this transfer map in group cohomology. So you can understand it from a construction in algebraic topology. This map is not a ring map, that's important. It's just a map of modules. And from the point of view of the cohomological algebra, is because, or this is because it's contracted directly at the level of cochains. It doesn't come from an actual map from the topological spaces. You just construct a morphism between the cochains, the other way around, just average, make the average of all the preimages and you add them. Yeah. And so it's not a ring map, it's just a module map. Yeah? But it's a morphism of, but it's not only of modules, it's a morphism of homology of G modules. What I mean, how it comes that this is a module over the cohomology of G? Well, just because of the restriction map. Yeah? So if you have a subgroup, I will use this notation, restriction KG, for the map that goes from the cohomology of G to the cohomology of K. And that gives you a structure of cohomology of G module on the cohomology of K. You want to take an element of the cohomology of G and you want to multiply by an element of the cohomology of K. You take this element, you apply these morphisms and you multiply. Yeah? And one important feature of this transfer map is that it's a morphism of cohomology of RG modules. And this, when you write it down, it's called Frobenius reciprocity. Yeah? When you write down what it means, it's what it's called Frobenius. Reciprocity. Yeah. Okay. So when you take all these restriction maps and all these transfer morphisms, all these morphisms all together, what happens is that the cohomology of G is what is called a Mackey functor. It comes from a contravariant functor and comes from a covariant functor, and the compositions, they satisfy certain relations. So let me describe the relations that they satisfy when you compose transfer and restriction and the other way around. Yeah? Okay, so First one. We do first restriction, then transfer that goes from the homology of the G, homology of K, homology of G. So this composition is multiplication by the order of the coset G, K, by the index of K into G. And this is already quite important, gives you a lot of information about the cohomology of a finite group, just this formula. Yeah? So let's see some consequences of. Well, for example, and here the choice of the coefficients is important. Here where we see that different coefficients will allow us to see different information. Yeah? Because multiplying by this number could be 0, could be an isomorphism, yeah, or none of those. Yeah. So depending on the choice of R, because this number is fixed, it's the index of K and G, and then you play around with different coefficients, and then you will get different properties, right? So for example, well, the first thing is that if this is invertible in R, this is an isomorphism, so the first map is injective. So what you see is that this is injective. So the cohomology of G injects into the cohomology of the subgroup. So if you take, for example, now you also can play around with several subgroups. There is a subgroup which you always have, which is the trivial subgroup. So what happens if K is the trivial subgroup? Well, you can. I didn't say anything, but you can imagine that the cohomology of the trivial subgroup, the classifying space for the trivial subgroup is a point, and then the cohomology is 0 in higher degrees. Yeah? So if K is the trivial subgroup, then multiplying by the order of G is 0. That means that the cohomology of G is annihilated by the order of the group. Yeah, so that means that this is 0. So it's all torsion. Right? And well, in particular, if you take R to be Q, if you take R to be Q and you combine with the previous one, it turns out that the cohomology of G is trivial with rational coefficients. So this is just from this formula, you already get a lot of information. Well, some properties of the group cohomology. Maybe it's not a lot, but it's, and then it's the first place in which you see, for example, whether the role of R is important. Yeah? So what will be, so what will be interested is that is taking, if you take K of the trivial group, we will be interested in coefficients. If you want to isolate the information of this cohomology at a prime, if you want to look locally, just prime at a prime, since there is no rational information, essentially you are reduced to look prime up at a prime, which torsion appears and how is it. Then you can just look at coefficients, just p-local coefficients or FP coefficients. Yeah? So for most of my talk, now I think, yeah, I will fix R to be FP, where P is a prime which divides the order of the group. Yeah? And we'll try to see, we'll try to compute as much as possible of the cohomology of G with FP coefficients. So if you fix a prime P, then you can also make a choice of a special subgroup for G. So when you fix a prime P, each finite group has a CLOP subgroup. Well, has more of it. It has a conjugacy class of CLOP subgroups. It has maximal P subgroups, and they are all conjugate to each other. So I can just take S to be a CLOP subgroup of G. In that case, this index is prime to P. Therefore, it's invertible in FP. So when you look at this restriction that goes from the homology P so that the homology of a finite group embeds injectively, can be seen inside the homology of a finite P group, and it's yellow. Then we would like to say something about the image of this map, because if I describe the image of this map, I've computed the homology of G. For this, I need another formula, which is the formula that goes the other way around. I don't know. Yeah, I'll try to fit it here. So what happens when you have H, K, you have two subgroups of G, and you want to do first transfer and then restriction. Yeah, that starts in the homology of, so transfer goes in the right direction for the groups. That's how I remember. So you start with homology of K. Well, here I could, well, I can write R. Yeah, so R into the homology of G, and then the homology of H. And that has a formula which is not as simple as this one. Okay, I'll try to describe it to you because I might need it in some forthcoming lecture. So the situation is the following. I have this rule to try to remember how it goes. You have H and K, they are subgroups. Yeah, and then here, I would like to fill this bottom, and then they do not intersect, might not intersect, but you take the conjugates of K, no, I did it the other way around, the conjugates of H, and I conjugate, and I intersect with K. Yeah? So you look at H, you have a diagram. So you take G's for which the conjugate of H intersects K. And then you look at all these possible intersections. Where does it come from? It comes from when you look at this G mod H cross G mod K. This is a G space. This is a G space. It's a finite G space, is an orbit. This is a finite G space, is an orbit. Take the Cartesian product, that's a finite G space, take the diagonal action. So if it's a finite G space, it must decomposed as a disjoint union of orbits, right? I only need to compute how many orbits and what's the isotropy subgroup of each orbit. And that's which this double coset formula does for you. So you take a double coset, and then just decompose as G mod and this is what fits in here, and then you have to look around. So if I do first transfer and then restriction, I start with H. This is I think it's G inverse HG. Yeah, I think that's what what I try to follow this convention. When G is on the right, G is on the right when I conjugate. And when G is on the left, I put G on the left. Yeah. So, yeah, so. Yeah. Oh, yeah, so, yeah, exactly. What I wanted to write is G minus 1. Yeah, so, yeah, this is my way to remember it's conjugate and then inclusion. So I write this symbol with the conjugation next to it. That means that it's not just an inclusion, that it's just you conjugate and you make an inclusion. And that helps to remember the formula. And then the formula goes like this. Yeah, so this is this path, right? You transfer restriction, and then it has to be equal, to the sum of all the other possible paths going down. So it's the sum. And what you do is you do a restriction. I'm messing now. So, no. So I have to conjugate. The conjugation should go in the middle, but I think they just commute. Yeah. So. Oh, I'm going the other way around. Yeah. So I'm not ambidexterity. I mean, I cannot deal well with right and left at the same time. Yeah, sorry. Yeah, so yeah, that goes this direction. Now I'm going this direction. So I restrict, and then I conjugate, and I transfer, right? So I restrict from K. The subgroup is K intersection QK, and then I conjugate, and then you are ready to transfer back to H. And now you have K, G, minus 1, H, and H. Yeah. Well, I'm not sure, but you understand what I want to do, right? Yeah. Oh, it's the mapping using cohomology. It's the conjugation, the mapping using cohomology by the conjugation. Right? And this is the formula. This is called the double coset formula. And it plays an important role in describing the image of this map. And that's so R, I'm back to R being FP. Yeah. So the theorem that it's due to Cartan and Eilenberg describes the image of this restriction SG is, and now I have to describe the elements which go there. This is okay. So the name I use is the image is the, I will write the name and I'll describe what it is. It's the stable elements. And let me describe. Yeah. So you take we say that an element in the cohomology of S is stable if the following happens. You take the P subgroups of S, you have the cohomology of S, you have the P subgroups of S, and you can start applying restrictions to all P subgroups. Yeah? So you start with element of the cohomology of S, and by applying restrictions to all subgroups, you can kind of propagate it and get an element in the cohomology of each subgroup. Right? And there are situations in which you have two choices to fill some gap. Right? So you have S, and you have P, a subgroup of S, and then you might have another subgroup of S, which is conjugate to P by an element of G. So you can have here a conjugation. So when you apply the cohomology, you take the cohomology of S, you have the cohomology of P, you have the cohomology of the conjugate, and then here you have this map induced by conjugation, right? This triangle do not commute, right? So if you have a star with X, you can look at the restriction SP of X. You can look at the restriction of S conjugate of PX. But then you have another option for this. You could just move this up using the conjugation. So for the cohomology of P, you could have kind of two natural choices. One, if you just restrict for P, and the other is you restrict to a subgroup, which is conjugate to it, and then do CG star. And then an element is stable if each time that you are in this situation, the morphism induced by conjugation take this to this. Right? So it's stable if for each E and conjugate inside in S, so you have such a diagram. When you do, okay, so CG star of the restriction of S G of X is the same as G of X. Right? This at the beginning of the lecture, I said that conjugation by an element of G induces the identity, but induces the identity in the cohomology of G. So this is not the identity, right? Because G does not belong to P. Right? So an element is stable if each time that you are in such a situation, this element gives you no choice. I mean, it's stable, it's compatible, both with restrictions and with all possible conjugations that you have inside your subgroups. Right? And so if S is normal, well, if S is normal, then, I mean, the quotient group acts on the cohomology of S. And then the cohomology is just the fixed points. Yeah. And then the theorem, it's, I mean, the other observation is that the restriction from G to S of the cohomology of G, we know that this is injective, so this is inside the cohomology of the silo. This is contained in the stable elements. And the reason is the following, is that these diagrams do not commute. But if I have G here, then I have this inclusion. If I write, sorry, if I write G, then this map, I can extend it to CG. And then this diagram commutes. And this induces the identity on cohomology. So from the description of the stable elements, you know that the cohomology of G has to sit inside the stable elements, which And then the double coset formula essentially tells you that the other way around, that if you have a stable element, sorry, I'm going to travel to the other side. So if you have a stable element, essentially means that you can get rid of this conjugation in the middle. And then you can get your element as the restriction. You can transfer all these elements and their restriction will fit. I mean, it's just playing around with the formula. So these are the stable elements. So I'm going to rewrite this theorem in a more categorical form, right? So let's consider the following category. Consider the category. I want to encode all these compatibility conditions as in terms of a limit of a functor in a category. So I want to encode all these compatibilities inside a category to give a description of these stable elements. Consider this category. I call F as G, where the objects are just subgroups of S. Yeah, you fix a silo and you look at all subgroups of S, they are P subgroups. And morphisms, well, morphisms will be group morphisms induced by conjugation. What I mean is that the morphisms from P to Q are group homomorphisms from P to Q induced by conjugation. In particular, that means that the conjugate of P is a subgroup of Q. But I only keep track of the group homomorphism, not the element. So this is a subcategory of the category of groups. The objects are groups and the morphisms are group homomorphisms. And then I can write if I take all restrictions from P to G along all subgroups of S, that goes from the cohomology of G. And then, well, you take all the restrictions, so you land in the product of the cohomologies of all the P subgroups of S. This is injective, because if you have S, for S in particular is injective, so this is injective. And the stable elements formula tells you that this image is all compatible tuples with respect precisely these group homomorphisms and inclusions. Right? So this is the limit of this functor. And the stable elements formula tells you that you can describe the cohomology of any finite group in terms of the cohomology of finite P groups and some compatibility relations which are just described by the internal group structure of G, which subgroups you have and how they conjugate to each other. Right? Yeah. So in particular, it says that if you could have two groups, G and G prime, with exactly the same structure at a prime P. Maybe different at different primes, but it would be that at prime P, they have the same structure. Then this is telling you that they will have the same cohomology, for example. Right? So the group cohomology is determined by this. This is called the P local information of the group G. Essentially, it's determined by P subgroups and their normalizers. And then you have this result. Okay. Well, it's, I didn't say the name, but it's called, yeah, it's called the fusion category. Of G at P. Yeah. So when subgroups are conjugate inside G, sometimes it's called that they are fused. And then this is called the fusion category, right? Oh, it's in the background because S is a P silo. Yeah, yeah. Sometimes there is, yeah, I fix P and yeah, but yeah, you are right. That's for example, what I think, yeah, he mentioned this case of if the silo is a billion, then the normalizer of the silo and G have the same structure, and then they have the same group homology. And there are several situations in which this happens. There's some, it's called Swan theorem about groups with a billion silos. Yeah. No, all the different S are conjugated to each other. Yeah, so you have two different silos, they are conjugated to each other, so you can translate the structure. So the structure is the same. And in fact, you could forget about S. So I wanted to make this comment. You could, just because I was fixing an S to detect the stable elements, you could just not use S and just forget about S here and take all P subgroups, and you take all P subgroups, and then you define the same, and then here you have a bigger category, and it gives you the same. So you can just, at this point, you could get rid of S and just work with all P subgroups of G. Is it? That's okay. So that's what we learned from. And then, so let me check. Oh, wow. Okay. So examples. Yeah. Well, if you take a course on group homology, so the first example is the trivial group, and then the next example are cyclic groups, right? And you compute the homology of cyclic groups from the definition. So you construct the resolution of Z as ZCP modules with free blah, blah, blah. And then you can do it geometrically using the fact that a cyclic group acts freely on a polygon, moving the vertices and the edges. And then you can think that it's acting freely on a simplicial space. And then you can take the 0 simplices, 1 simplices, and then you know that that's an S1. So that gives you a short sequence. We have Z, Z of G, Z of G, Z, and we have some morphisms that you get from the geometric structure. And then the strategy is that in that case, you can splice together all these pieces, and then you get that the homology of a cyclic group is periodic, for example. Okay? So you combine topology and geometry, but then, yeah, so let me write the homology because I will be interested in it. So you take an elementary abelian P group, that means that P to the N, and then the homology of P with FP can be computed well using some Kunev formula and what I just described before that you can explicitly do with cyclic groups. Then you have FP x1 xn of degree 1, and this is for P equals 2, so I can write 2 here. And then you have FP x1 xn tensor and exterior for P odd, and then the degrees of the x and the degrees of the y's is 1. So this is the first example that you just explicitly compute. This is a graded commutative algebra. That means that it commutes up to a grading. There is a -1 to the product of the order of the elements that you want to commute. Yeah? So the elements in odd degrees, they square to 0, yeah? Because of these formulas for P odd. Yeah? And So a note that I might use, well, later or Monday, depending, is that if you just look at the cohomology in even degrees, then it's commutative on the nose. Right? So if you look at the cohomology of G in even degrees, it's just commutative. Yeah? That's an observation that I might use later. And then, well, when you want to try to do more computations, it's not that easy. So my experience in a course of group cohomology is that after this point, you learn about a spectral sequence and short exact sequences. And essentially, you make more computations building up from elementary abelians. For example, D8, the dihedral group, is an extension of Z2 cross Z2 and Z2. And then if you, for example, if you have topologies, you have vibration when apply classifying a space, and you have a set of spectral sequence, and you compute from there. And the same for Q8, for example. Yeah? So these are the next examples that you would like to do from elementary abelians, D8 and Q8, and then you build from there. So computing the cohomology of a finite group, even if you have, I mean, this reduces to computing cohomology of finite P groups, but the cohomology of a finite P group is not by any chance easy to compute. Essentially, you have elementary abelians, and from here you have different techniques, right? So, yeah. So, but sometimes you can get information which is not, it's qualitative information instead of just computing. Let me give you an example that will be also relevant. Okay, so the cohomology of a finite group, okay, I can write is Noetherian. This R is Noetherian. So how do you prove such a statement? Well, so let's do RFT. So this is due to, it has several proofs, but Benkov and Golot and there's a third name that now I don't remember, but Evans, yes, exactly, thank you, yeah. So Andrea, you have two strategies. One strategy is, well, you know that the cohomology of Z mod P is finally generated, it's Noetherian, fine. And then your next step is to go to finite P groups by induction on the order of the group. And what do? You use the property that the center of a finite P group is not trivial. Yeah. So you have strategy one. Yeah. So induction on the order of P, if P is a finite P group. And the induction goes by using that. You take P, the center is non-trivial, so you have a central extension. So the starting point of the induction is Z mod P. And then you take you make induction along the sequence. This is a finite P group of order less than P. You know that the cohomology is Noetherian. This is an abelian. This is abelian. So instead, you can say that the first step is that for abelian finite P groups is Noetherian because you can explicitly compute and then use the spectral sequence. Right? The strategy two, which I like and I will use so later, is the following. I will make a note. I'm dealing with finite groups, right? But what about compact Lie groups? What's the group cohomology of a compact Lie group? You have two choices because G itself as a compact Lie group is a topological space. So it makes sense to look at the cohomology of G. But that's not the right choice. The right choice is to look at the cohomology of the classifying space of G. So when we want to make an analogy of group cohomology in the wall of compact Lie groups, we take the cohomology of the classifying space. So, so if G is a compact Lie group, we look at the cohomology of the classifying space. And there is also a building block to understand the cohomology of Lie groups, which is the unitary group. Right? And there is a particular example, which is the cohomology of the classifying space of the unitary group is a polynomial algebra on n generators of degree 2. This is other Chern classes for in fiber, the characteristic classes. And the computation goes along by fibrations. BUn-1 maps into BUn, the fiber is a sphere, and then you go along the sequence. But how I'm going to use this for a strategy 2? Strategy 2 is, well, instead of reducing to finite P groups, well, I didn't finish. Then when you have the result for finite P groups, you use the transfer and to deduce that the cohomology G is Noetherian, using that the transfer is a map of cohomology of G modules. I mean, and then finally use the transfer. But for strategy 2, what you need to do is you need to embed G or find a group monomorphism from G into the unitary group, right? And this is, you can use the regular representation, for example. So G acts on itself. G is a G set. So you can take a complex vector space generated by the elements of G, and then G acts on this complex space by permutation matrices. So, and then, well, you have to make it unitary, you have some reduction, but you can embed G into UN, right? And then one looks at this fibration. You look at the map induced for classifying spaces from G into UN, and the fiber is UN mod the action of G. UN is a G space via this action, and then you look at the orbit space. This is a Poincaré duality manifold. So, and then when you look at the third fibration, I had third spectral sequence, because this is finite, it just collapses because it has a finite number of rows. And each A2 term is Noetherian, and then you take subquotients, it's Noetherian, and then you end up. Yeah? I'm not going to give more details, but I'm happy to tell anyone who wants to know more about these strategies. So that's something that you know about the cohomology of G, even if you cannot compute explicitly. And so that's one thing. And then so we know that we could compute the cohomology of G by just computing this right-hand side, but this right-hand side is not easy to compute because the cohomology of P subgroups are not easy to compute, but we know the cohomology of elementary abelian subgroups. So we can just consider the full subcategory where the objects are only the elementary abelian subgroup. Just forget about every subgroup which is not elementary abelian. Just keep the elementary abelian subgroups. And so I consider this the family family of elementary abelian P subgroups. And then it makes perfect sense to just look at the cohomology of G and then consider only the elementary abelian subgroups in Z zero. I will make the same remark as before. You can just take all elementary abelians. It makes no difference, right? Every elementary abelian will be subconjugated to one in this fixed silo, but if you take all of them, it makes no difference. Okay? And then you look at the limit, and here you take F epsilon G and here you take all, you take all restrictions. So now on the right-hand side, at least I know the cohomology of elementary abelians. Computing this limit, well, might not be easy, but it makes sense to look at this, right? What can we say about this map, right? So does it help? Can we detect anything, or it just gives no information? So that's the content of Quillen's F-isomorphism theorem, the theorem in the first part of this series of papers, these two papers, right? Let me give you an example of, for example, if you take Z mod e to the n, where n is bigger than 1, right? There is only one elementary abelian sitting inside it, right? Z mod p. There are no other elementary abelians sitting inside. So in that case, this family is just consists of one single element, and it's abelian. So all conjugations are the identity. So when you describe this category, it's just one element corresponds to Z mod p sitting inside Z p to the n. So essentially, in that case, this map is just a restriction to Z mod p. And you have the, yeah, I will. So in that case, you have homology of Z to the n Fp into the homology of Zp Fp. And then this is known. So it's polynomial tensor exterior, degree 2, degree 1. And this is, it looks the same. But the map that goes from here to here sends x1 goes to xy prime, but y1 goes to 0. That's how it goes. You have to believe me. Yeah. So that's how it goes. So this is not even it's an example in which you have two groups, for example, so you have two groups which the cohomology algebra is the same. The difference lies in something which is called higher operations that I'm not going to discuss. But from the point of view of commutative algebra, I mean, it's these two algebras, they look the same, right? But the map that goes from one to the other, it's not an isomorphism. It has a kernel and a cokernel. And the kernel is just the elements, is this element here. So it's the ideal generated by this element, which are nilpotent. And if you look at the cokernel, if you look at the elements here, this is not any element. This is squares to 0. And then if you multiply a power of this by some of these y's, when you square that goes to 0, well, I don't know if it's a good example, but what I want to say is that any element up to some power, it's in the image of this map. Yeah? And this is exactly the content of the theorem of Quillen. Another example, for example, is the Q8, the dihedral group on 8 elements. It has only one elementary abelian, which is the center, which is at mod 2. So you can imagine that this map will not give you much information. But it tells you something, and this is what Quillen's theorem is about. Let me check now. Okay. So yeah, so Quillen's F-isomorphism theorem, you have this map rho that goes from the cohomology of G into these stable elements restricted to elementary abelians. So this has a following property. There exists n, a natural number, such that for all, such that if x is in the kernel of rho, if it goes to 0, that means that you have an element of G that it's invisible when you restrict to elementary abelians. But you know that it's going to be detected by some subgroup because of the stable elements formula. It cannot just go to 0 on all p subgroups. But if you restrict to elementary abelians, you don't see this element. Right? So if you have such an element, then this power is in the kernel. Oh, 0, yeah, sorry, yeah. If something is in the, exactly, yeah, so I got it right the first time. Yeah, it's 0. So that means that the kernel is nilpotent. And one point is that this n is uniform. It does not depend on the element. There exists an n such that for all x in the kernel, this power is 0. Yeah? And what about the image? So this is telling you something about the kernel of this map. What about the image of this map? So now there exists an M such that, well, this map is not surjective. I mean, the one we had, this example was not surjective. Well, it's not surjective, but it's not up to taking powers. That means that if you take, this is the name such that if x, if you have an element in this limit, then x, well, in fact, it's more precise, is x, well, let's write x to the m is in the image of rho. And in fact, this m turns out to be some power of p, but I will not care about this at this point. So this is what the information that you get from Quillen's theorem. Sometimes this is an isomorphism. Sometimes, and these are called Quillen groups. A Quillen group is a group for which this morphism is an isomorphism. So there are groups in which the cohomology is completely detected by elementary abelian subgroups. But it's not always the case. So well, I wanted to go through the key points of the proof. Maybe I will just say a few words. I will leave it for next talk. Yeah, so maybe I will make a comment. I'm not sure how much. Okay, I'll do the first step, which is short. Is it clear, the statement that we want to understand? Okay, so the idea, there are more than one proof of this statement, as I said at the beginning. So the first proof that appeared in this paper by Quillen, the spectrum of an equivariant cohomology ring, is the one that uses more homotopy theory and geometry. Then using a search theorem, they found a proof completely in the cohomology of groups algebra setting, right? Yeah. So the proof has several steps. So how does the proof? So my goal is not to give all the details of the proof, but I think there are some key steps and ideas which are worth knowing. Right? So the first one is just sometimes you want to prove a statement, and it's better to go in a more general context and not to be in this restricted context. And that's what Quillen does at the beginning. So in fact, he doesn't prove the statement for G. He does it for, he takes G spaces and he looks at the Borel cohomology of these G spaces. Right? So the first step is just go more general. So the setting is take X, a compact G space. In fact, he even goes a bit more general. He goes with some paracompact spaces with finite cohomological dimension, but I will just keep for compact spaces because I will not go into the details. But in that case, it takes X to be a G compact space, and then you need to modify this indexing category here to take into account the action of G in X. Right? And then defines another category which takes into account X and the G action. And the objects are it's an elementary abelian subgroup of G. It's a pair in which you have E and C is a connected component of the fixed points of X. Right? So this is a pair. This is an object. And if you have another object, what's a morphism between these two pairs? Well, remember that the point is that we would like to recover this statement when X is a point, right? And then if so the morphism from E to E prime, when you project to E prime, they must coincide with the ones here, right? So it's some G. It's conjugation by an element of G such that CG sends E to E prime, yeah, and you need some compatibility with these connected components, so that when you translate the connected component C, then this is contained in the connected component C prime. Yeah? So you need some compatibility within these two. So when X is a point, then there is no C, and then you just have the previous. Right? And then he deals with this category, and then the statement is then you go from the what's this? I didn't say what it is. This is the cohomology of the Borel construction on X. So then this goes to the limit over this category, and then here you have the homology of DE, and this is rho, and then he shows that this is an F-isomorphism. And now I've used the word F-isomorphism, which I didn't use before, but it's in the title. So if you have a morphism which satisfies these two properties, we say it's an F-isomorphism. And this is the first step. Say, just try to prove it in a more general context, such that then when you take X as a point, you specialize to the result that you want for group homology. And then there are two steps. So the first step will be to reduce to the isotropy subgroups of G, which has some idea about some spectral sequence having a vanishing line, something that vanishes from some point. And there is another step which goes from reducing from isotropy subgroups through elementary abelian, and it uses again the unitary embedding. So I will try in the next talk to give the key ideas in these two steps, and the goal is to have the exercise to see, well, could it work for other cohomology theories? And there is one cohomology theory in which it will work by replacing the family with another family, which is the G equivariant K theory. Yeah? And then I will try to explain how the G equivariant K theory just mimics what happens with multiple cohomology. There's only one point in which you cannot use elementary abelian. You have to use cyclic abelian subgroups, but that's it. Okay, so thank you.
Questions, comments?
In that example that you gave with Z mod PZ, so your category FSG is going to be just a single object and only the identity morphism?
Here?
The board before that.
Here?
Yeah, so yeah. FSG is just the terminal category?
Yeah, G, this is the one just with elementary abelians.
Right, so when you take the limit in the diagram above that, for the map row that you've written above that, yeah. Is that limit not going to be just H star G FP? So
yeah, I mean, in that case, yeah, so in that case, you have this limit. I mean, the category is just one object with no morphisms. Yeah, you just have the cohomology of Z mod P.
Right. So if the map is restriction, right.
This map. Yeah.
So if the map is just restriction onto each component, shouldn't restriction be identity in this case?
No. That's even if they have the same. I mean, this is not the identity.
Okay, so
the map induced from the inclusion of ZP into ZPN is not the identity. This can be seen starting with ZP square, right? And then you have ZP, ZP square, ZP, yeah, and then you have a fibration that computes the cohomology of ZP square, and then from there you see that this element it survives, but then some element goes to zero. I mean, this is, you need, the way I know to show this is using the short exact sequence ZP, ZP square, ZP, and then you prove it from ZP square, and then you do inductively that the polynomial generator goes to the polynomial, but the exterior one goes to zero because of the behavior of the spectral sequence.
But if the restrictions are supposed to be functorial, then shouldn't they take identity to identity maps to identity maps?
Identity maps?
As in the map, the inclusion of Z mod P into Z mod P is identity, right?
Oh, okay. Yeah, if n equals 1, yeah, but n, yeah, n is...
sorry, I didn't see the n.
Yeah, for n equals 1 is the identity. Yeah, but you need to take n bigger than 1, and then it's where this pattern starts to happen. Yeah.
Thanks.
Any other questions? If not, let's thank the speaker again.
Thank you.